In this lecture, I am going to talk about the connection between sets of vectors and matrices formed using these vectors as their columns. First, I would like to remind you some important definitions and properties which we are going to use in the future. And the first definition is following. A matrix Q is said to be orthogonal if its columns Q1, Q2, and Qn, all of them transposed, form an orthonormal set in Rn. So, here it's better to say that orthogonal matrices are orthonormal because the columns form not just an orthogonal but an orthonormal set of vectors. The next set of properties I will state as a theorem. Suppose that Q is orthogonal matrix n by n. Then property 1 states that Q is invertible with property that inverse matrix Q equals to transposed matrix Q. Second property states that for any vectors x and y from Rn, the product between transposed product of vector x multiplied by matrix Q from the left and product of vector y multiplied on matrix Q from the left equals to transposed vector x multiplied on vector y. Property 3 states that for any vector x from Rn, L2 norm of a product of vector x multiplied by matrix Q from the left equals to L2 norm of vector x. This particular property immediately implies that L2 norm of matrix Q equals to 1. And the last property, any invertible matrix Q with a property that inverse matrix Q equals to transposed matrix Q is orthogonal. And below I provide just definition what the inverse matrix is, just to remind you that n by n matrix A is said to be non-singular or invertible if n by n matrix A of this form exists with the property that product between these two matrices, and doesn't matter from which side they multiplied on each other, equals to identity matrix. The matrix A minus 1 is called the inverse matrix of matrix A. And matrix without inverse is called singular or non-invertible. It's just a reminder for you. Now let's solve an example. Show that the matrix Q with following form, formed from the orthonormal set of vectors, is an orthogonal matrix. So what we are going to do is we are going to find the product between matrix Q and transposed matrix Q. This is our matrix Q. This is our transposed matrix Q. Just in order to remind you what means transposed, we exchange columns and rows. First column becomes first row, second column becomes second row, and so on. If we multiply these two matrices, we will get identity matrix. Then, by corollary, from, let's say, chapter 6 from your textbook, which states that suppose that both A and B are n by n matrices with either product AB equals to identity or product BA equals to identity, then matrix B equals to inverse matrix A. And this corollary is sufficient to ensure that our matrix Q transposed equals to inverse matrix Q. So our matrix Q is an orthogonal matrix. Example is solved. The following definition provides the basis for many of the techniques for determining the eigenvalues of a matrix. Let's formulate this definition. Two matrices A and B are said to be similar if a non-singular matrix S exists with the following property: matrix A equals to the product of inverse matrix S multiplied on matrix B and multiplied by original matrix S. Let's use this definition in the next theorem. Let's formulate theorem 2. Suppose A and B are similar matrices, and by definition matrix A equals to the product of inverse matrix S matrix multiplied by matrix B and multiplied by original matrix S. And assume that lambda is an eigenvalue of matrix A with associated eigenvector x. Then lambda is an eigenvalue of matrix B with associated eigenvector Sx. Now let's prove this theorem. Suppose that we have vector x which is non-zero, such that the following equality holds. And it holds because of the definition of the similar matrices, because we assume that A and B are similar matrices. And we also know that lambda is an eigenvalue of matrix A. So now what we are going to do, let's say equation 1, we are going to multiply this expression 1 on matrix S from the left and write down expression 2. Then we can notice that the product of S and inverse S, it's just identity matrix, because I just provided you the definition of non-singular matrix S. And we can write down expression 3 as follows, which is left side and right side. Since our vector x is non-zero vector, and since matrix S is non-singular, it implies that their product is also non-zero vector. So, and by definition of eigenvector, it immediately implies that Sx is an eigenvector of matrix B, corresponding to its eigenvalue lambda. So this is exactly what we wanted to prove. Theorem is proved. Now let's formulate one more theorem. An n by n matrix A is similar to a diagonal matrix D if and only if A has n linearly independent eigenvectors. In this case, D equals to the product of inverse matrix S multiplied by matrix A and multiplied by original matrix S, where the columns of matrix S consist of the eigenvectors and the ith diagonal element of matrix D is the eigenvalue of matrix A that corresponds to the ith column of matrix S. Here I would like to mention that the pair of matrices S and D is not unique, and you can easily show it by reordering the columns of matrix S and corresponding diagonal elements of matrix D. If you do all calculations correctly, you should get a different pair of matrices. Next, in previous lecture, I formulated you the following theorem. If A is a matrix and lambda 1 and lambda k are distinct eigenvalues of matrix A with associated eigenvectors x1, xk, then the set of these eigenvectors is a linearly independent set. Similarly, we can formulate the following corollary. An n by n matrix A that has n distinct eigenvalues is similar to a diagonal matrix. So, let's formulate one more very important property, and which calls similarity transformation. Now suppose that we have matrix A, which is similar to triangular matrix B, and in order to find our eigenvalues lambda, we should solve this equation, and we can get solution only if and only if lambda equals to diagonal elements bii of matrix B for some I. And the next result describes a relationship between arbitrary matrices A and triangular matrices. And this transformation calls similarity transformation, or Schroze theorem. Let's formulate it. Let A be any arbitrary matrix. A non-singular matrix U exists with a property that matrix T equals to the product of inverse matrix U multiplied by matrix A and multiplied by matrix U, where T is an upper triangular matrix whose diagonal entries consist of the eigenvalues of matrix A. So, just to remind you that matrices with a property that L2 norm of the product of vector x multiplied by vector u equals to L2 norm of vector x for any vector x are called unitary matrices. And U is a unitary matrix. And this particular theorem, this is an existence theorem, which ensures that the triangular matrix T exists, but it doesn't provide us the way how to find this matrix. And of course, in order to find this matrix, we need to know the eigenvalues of matrix A. And in many cases, the matrix U is also very difficult to find. So let's see how we can simplify this idea. Since the similarity transformation matrix sometimes difficult to compute, we need to find the way to simplify our calculations. And one way to think about it is to introduce symmetric matrices. And these matrices significantly reduce the complication, because in this particular case, the transformation matrix will be orthogonal. Let me formulate following theorem. Theorem 5. The n by n matrix A is symmetric if and only if there exists a diagonal matrix D and orthogonal matrix Q with a property that matrix A equals to the product of matrix Q multiplied by matrix D from the right and multiplied by transposed matrix Q from the right. Let's prove this theorem. The statement of the theorem implies that we should prove this statement in both directions. So, first, let's suppose that our matrix A can be represented as a product of three matrices, Q, diagonal matrix D, and transposed matrix Q, where Q is orthogonal matrix and D diagonal matrix. This is given in this particular case. And we're supposed to prove that matrix A is symmetric. How we can do it? So, let's rewrite expression that is given and transpose it, left and right side. Then, at this point, we will apply some properties. Let's say transposed matrix A, and if we transpose it again, it's going to be matrix A. And another property, if we consider product of two matrices A and B, and we want transpose this product, it's going to be transposed matrix B multiply on transposed matrix A. And these properties we will use here at this point. So here, let's say property 1, property 2. By property 1, this is matrix Q. If we transpose matrix 2 times, we will get our original matrix. This is what it says. And the product of matrices, if we also apply it, here we can get this final expression. And by our assumption, this is simply matrix A. So what we did in this part, we proved that our transposed matrix A equals to our original matrix A by performing certain calculations. So the conclusion is that our matrix A is symmetric matrix. And below I just remind you the definition, what means symmetric. A square matrix N A is called symmetric if A equals to its transpose matrix. Now let's prove second part of our theorem. What we should prove here, we should prove that every symmetric matrix A can be written in this form. Now this is given. A is symmetric, and this is what we should prove. Consider the distinct eigenvalues of matrix A. By definition of eigenvalues, we can write down this expression and this expression. And let's say that lambda 1 doesn't equal to lambda 2. So, by definition of a symmetric matrix, our matrix A equals to transposed matrix A. So, by performing some calculations, it can be done differently, but one way to think about it, we can consider, for example, this expression, and let's say we can transpose it, multiply on V2 from the right, and then we can perform some calculations And we can get that since this difference should be equal to 0, and we recall that transposed matrix A equals to matrix A, and we should also remember that lambda 1 and lambda 2 are distinct eigenvalues, which means that difference doesn't equal to 0. And it immediately implies that this product equals to 0. So, which means that we have orthogonal vectors. And by normalizing our orthogonal eigenvectors, we can get orthonormal set of vectors for distinct eigenvalues. In case if we do not have distinct eigenvalues, we will deal with certain subspaces of eigenvectors, and for each of multiple eigenvalues. And then we should apply Gram-Schmidt orthogonalization process and find a complete set of orthonormal eigenvectors. So this theorem is proved. Let me formulate one more corollary. Suppose that A is a symmetric n by n matrix, and there exist n eigenvalues of matrix A that form an orthonormal set, and the eigenvalues of matrix A are real numbers. Let's prove this theorem. First of all, in this case, it's given that matrix A is a symmetric matrix, which implies that we can use a theorem from previous slide. And it implies that matrix A can be represented as a product of matrix Q multiplied on matrix D and multiplied on transposed matrix Q. What means matrix Q? It's orthogonal matrix, and matrix D is a diagonal matrix. So, what we can do is following. We consider this expression in the blue box on the right side, and let me change color. And now first multiply this expression on Q from the right. Let me write this one. And we should notice that this product is just identity matrix. Then we multiply on transposed matrix Q from the left. And again, this is an identity matrix. And we exactly see this expression here and this expression here. Then, in order to do this step, we should recall theorem from previous lecture, which states that there are certain properties of the orthogonal matrix, and especially one of the property that if we deal with orthogonal matrix, the transposed matrix equals to inverse matrix Q. So, and that theorem from the previous lecture allows us to write this equality. From previous lecture. Theorem about properties of orthogonal matrix. So, now we can do the last step, and we can multiply our expression, last expression, left and right side on Q from the left. So again, we get identity matrix, and we have this last expression. Now, let's consider Vi with components Q, 1i, and so on, and I, be the ith column. Let me write it down. Of matrix Q. When we can write down this equality, and dii will be eigenvalue of our matrix A with eigenvector Vi. So again, in the blue box on the left side, I just remind you what means for matrix to be orthogonal. And the definition says that matrix Q is said to be orthogonal if its columns form an orthonormal set in Rn. This is a definition. So the columns of matrix Q, since it's orthogonal, are orthonormal. So the eigenvectors of matrix A are orthonormal. And this is exactly what we wanted to prove. First part is done. We proved it. So here, first part. Then second part. Now we want to prove that the eigenvalues of matrix A are real numbers. We should do some more steps. So now we should multiply our equation on the left by Vi transposed. And since D is just number, we can write it down as following expression, and then we should just analyze this expression. First, this is a real number, and second is also real number. And moreover, the product of these two vectors equals to 1. So our eigenvalue dii equals to this product, which immediately implies that it's real number, as well for each I between 1 and n. So theorem is proved. The next definition reminds us what the positive definite matrix is. A matrix A is positive definite if it's symmetric and if the product of transposed vector x, matrix A, and original vector x, positive for every n-dimensional non-zero vector x. So let's formulate one more theorem. This theorem establishes the relationship between symmetric matrix, positive definite matrix, and eigenvalues. The theorem states that a symmetric matrix A is positive definite if and only if all the eigenvalues of matrix A are positive. Let's prove this theorem. Since we have in statement if and only if, we should prove this theorem in both directions. So, first suppose that matrix A is positive definite. Also, suppose that lambda is an eigenvalue of matrix A with x associated eigenvector, such that L2 norm of vector x equals to 1. Then, by definition, because we assume that matrix positive definite, it's given, therefore we can use this statement. So, and we can write this inequality. At the same time, lambda is an eigenvalue, and by definition of eigenvalue, we can write down this equality. So, our lambda is just number, we can perform simple. We can take it out. And finally, this dot product of two vectors is just simply L2 norm, and our expression equals to lambda. And since our matrix A is positive definite, let me change color to give you, we have first inequality here and we have lambda here, which means that lambda positive. So the first part is proved. Now second part. So in order to prove second part, we should recall our corollary and the theorem from the chapter, I believe, 8 from your textbook. So, and in this case we have following. Suppose that our matrix A is symmetric with positive eigenvalues. Now this is given, that lambda greater than 0. So, by corollary, we have that if A is a symmetric matrix, there exist n eigenvectors of matrix A that form an orthonormal set. So, assume that our eigenvectors, like n eigenvectors, v1, vn, and this set form an orthonormal set by this corollary. At the same time, there is another theorem that an orthogonal set of non-zero vectors is linearly independent. So, for any non-zero vector x, exists unique set of constants, non-zero constants, let's say beta 1, beta n, for which we have this expression. In other words, our vector x can be represented as a linear combination of vectors vi multiplied by constants beta I. Let's say this is expression 1. So, the next step what we are going to do is following. We are going to multiply both sides of our expression 1 on product transposed vector x multiplied on matrix A. And we multiply our expression 1. So, and this is the result what we can get. Again, we take matrix A inside the summation sign. When we do some calculations, so here by definition of eigenvalues, we just replace this product A V with lambda V, and next step we replace this transposed vector x with formula 1, apply 1, just transposed, and we will be able to get this expression, let's say expression 2. Then we should recall that vectors v1, vn form an orthonormal set. Which immediately implies that the product of these two vectors equals to 0 when I doesn't equal to j, and equals to 1 when I equals to j. So, if we recall again that our lambda in this part are positive, this is our assumption, we can rewrite our expression and see what we can get. Here we deal with orthonormal set, this is 1. This product, because of 3, let's say apply 3, because when I doesn't equal to j and product equal to 0, product of vectors, and we just do not have these terms in our sum, therefore all what left is case when I equals to j, and in this case beta simply beta square. So, and since we deal with orthonormal set, L2 norm also equals to 1, and our lambda by our assumption positive, all positive, and entire product is positive. So our matrix A is positive definite. This is exactly what we wanted to prove. And the whole theorem is proved. So, all this theoretical background what I covered during the last 2 lectures, we will use later in numerical methods.